Hi everybody, I'm sitting in SFO airport and my flight is 3 hours delayed, so I'm going to make the video real quick. I apologize for the people going behind me on the moving walkway. But here we go. So you guys are taking the midterm tomorrow. Just wanted to remind you about growth mindset, specifically down here, reaching ever higher levels of achievement, thinking about all the good work that you guys did for your midterm 1 revisions and putting all of that good thinking into this exam, thinking about the critiques that you got and how you can improve, and thinking about overcoming some of the challenges specifically in taking this, preparing for this next exam and actually thinking about being successful. So I'm going to go through the study guide really briefly. The first part of the study guide focuses on the fossil record and biogeography and observational studies, which are all 3 lines of evidence that support evolution. The one that's missing off of this from the list we talked about is homology, which we talked about for the last midterm. So jumping into the fossil record, as you guys remember and got to see firsthand, fossils illustrate basically how organisms have changed over time and allow us to see what the similarities and differences are between organisms that once inhabited the earth and the organisms that we have today, and allow us to make all kinds of predictions. So we focused on transitional fossils. Transitional fossils allow us to observe or put together, I guess, observations of fossils that we find to piece together how major transitions happened on Earth. So we spent a little bit of time talking about the transition of life from land back into the water, which describes that of marine mammals, as well as the transition of life from the water onto land, which happened much earlier, 375 million years ago, whereas over here we're talking more in the order of tens of millions of years. So pretty different timelines, but both major transitions on Earth. In terms of cetaceans, that again is the biological term for whales. Whales are again evidence of this really complex transition back into the water. Whales have strong relationships to other mammals, including hippos. If we look at them on a phylogenetic tree, which now you should understand a lot better after building them in lab yesterday, we can see our timeline on the bottom. We didn't have timelines on the trees we built, but we see them on a lot of these widely used phylogenetic trees in education and also in research. So we see hippos and modern day whales share a common ancestor. Back about 54 million years ago, somewhere around 52 million years ago, this common ancestor of all cetaceans split. So we had a split in lineage, probably due to speciation, some sort of disruption of reproduction within major populations that led to lineages splitting in different directions. One lineage led to Pakicetus. We can see Pakicetus went extinct somewhere around 45 million years ago. That's why these branches are kind of cut off. Rhodocetus was another resulting lineage and descendant of this common ancestor, and so that guy went extinct around 40 million years ago. And then living cetaceans, and probably the most closely related animal in the fossil record that again went extinct a long time ago, 35 million years ago, they split about 40 million years ago, and this lineage here describes what eventually took us to living cetaceans, gray whales, humpbacks, and all their related cousins. So we can see that this phylogenetic tree allows us to think about these transitions by examining specifically fossil evidence and looking for anatomical homologies among the bones, and the similarities that we see in bones as well as molecular data allow us to place them on a phylogenetic tree like the one that we see here. Tiktaalik is another transitional fossil that shows us this transition of organisms, specifically vertebrate life from water onto land. So we see fish, Tiktaalik, and tetrapod shown on this diagram to kind of exhibit some of the similarities and differences. So we can see that fish have round heads, whereas tetrapods have flat heads. So Tiktaalik shows an intermediate form, which is this flat head with its eyes on top, We see some specialized fins in Tiktaalik, which is a little bit more similar to fish in that they have fins, but as we know, specialized fins eventually gave way to limbs, so again, an intermediate form here. Ribs we don't find actually in fish, we just find this backbone with no of those kind of like hanging bones off of it, which are ribs. We do find ribs in terrestrial tetrapods, and so those are just some of the examples that allow us to look at these intermediate forms and put together a better understanding of how this transition occurred. Again, Tiktaalik went extinct a long time ago, but this just goes to show you that an organism that went extinct a long time ago can still teach us a lot about organisms that are still around today, like amphibians, mammals, and other reptiles. Great. So that is the fossil record. You should also be familiar with some of the fossils that Larry brought. Maybe look back at the whale and the Tiktaalik videos that we watched together to examine some of these guys in more detail. And that's about it. In terms of biogeography, we talked really briefly about biogeography allows us to look at patterns of landforms and organism distribution across Earth to kind of work in harmony in observing this geologic evidence and this organismal evidence to better understand how geologic changes happened and how those geologic changes led to distribution of species that are still around now and species that have gone extinct. Last line of evidence, observational studies. So in observational studies, we particularly focused on MRSA and the rock pocket mice, of course. In MRSA, we read the article that's also available on Canvas if you want to look back at it, and we discussed this question here. We had a big, meaty discussion that hopefully you remember about that. And we revised this statement to make it more scientifically sound and more clear, and we talked about actually different ways that you could revise it to avoid any misinterpretations and spreading misconceptions. So we know that individual bacteria are constantly changing regardless of the environment due to mutations that happen at random and happen no matter what's going on in the environment. But the antibiotics are placing a selective pressure specifically on bacteria, and that's what can lead to something like antibiotic resistance. So takeaway from that is that variation in a population occurs due to random processes like mutation, and these random processes could cause any variation of a trait that could be viewed as good or bad or neutral. And usually when we're talking about good, bad, neutral traits, like there's always some sort of compromise, and we'll talk about that a little bit more. We also, of course, talked about the rock pocket mice, and I pulled this from the HHMI website. I like that these look like zombie glowing mice. Rock pocket mice are another example of evolution in action, and in order to track evolution, we of course look at allele frequencies. We could look at those in MRSA too. We didn't, but we did look at allele frequencies in mice to better understand how scientists track evolution. So, for instance, we don't just track allele frequencies at one point in time. We would track allele frequencies at many points in time. So we would look back at a same population in 5 years and say the p-value, the small p-value of this was 0.7. That means the frequency of the dominant allele, in this case dark, is 0.7, and then the frequency of the recessive allele is 0.3. Then we would look back in 5 years and see if those frequencies have changed at all. And in this particular example, we see that they have, and so that's evidence that evolution happens in a population. So the Hardy-Weinberg formulas, which I'll give you on the exam, are these: p plus q equals 1, and then p squared plus 2pq plus q squared equals 1. And I found a really great Bozeman video on allele frequencies that I'm in Hardy-Weinberg that I'm going to post, that does an amazing job of explaining like where these p and q values come from and why 2pq, for instance, is the frequency of the heterozygous genotype, and walks through some example problems. So since that video is already made and it's great, I'm going to post that along with this video. You might have found some practice problems at the end of the slide set on Hardy-Weinberg. Specifically, I think it was at the end of the observational studies slide set, the lab slide set actually, you'll see some practice problems here. So this is one that I thought would be worth going through. You've sampled a population in which you know the homozygous recessive genotype frequency is 0.36. So if you want to pause the video and think to yourself, what is 0.36 representing in terms of these variables in the formula, go ahead and do that and see what you come to. So hopefully you came to that 0.36 represents Q squared, which is the homozygous recessive genotype, and the Q squared value comes up in the second formula right here, which is really focused on genotypes. So the 0.36, if that's our Q squared value, then to get the frequency of the A allele, or to get Q, then all we would do is take the square root of it, and that would give us 0.6. To figure out the frequency of the dominant allele, we need the P plus Q equals 1 formula. And so to do that, we're going to add P plus Q equals 1, plug in 0.6 for Q, and we get 0.4 for P. Now to get the frequencies of the genotypes, big A, dominant, homozygous dominant, and then the heterozygous, we need to go to that second formula. And here we're going to reference P squared, and here we're going to use 2PQ. So if we plug in these values and we do P squared for this one and 2PQ for this one, then we get that P squared is 0.16 and 2PQ is 0.48. Then finally it says, what are the frequencies of the phenotypes? So hopefully remember that phenotype is what the genotype is expressed as. So in this case it would either be, well, we don't know. It doesn't tell us, but let's say light or dark. The phenotypes can be determined by basically adding up the genotypes. And we know that if there's a dominant phenotype, then we're going to get that from P squared, the homozygous dominant, and 2PQ heterozygous, because if the A allele is dominant to the little a allele, then that would mean that any heterozygotes would also have the dominant phenotype. So we'd get 0.64 for the first one, and then we'd get 0.36 for the second one. Another practice problem to check out in that slide set is this one, and this would be a really good one to walk through. Again, if you know that 40% of all butterflies are white, then you should pause the video and think about what number is actually given to you here and start with that. So if you pause it, think about that, then you should find that you actually have Q squared. That's 0.4, because that's the white phenotype, which if that's the recessive phenotype, it's going to be the homozygous recessive genotype that it's exactly equivalent to. So you can start with that and walk it through the rest of the problem. Okay, briefly we're going to look at these remaining topics. So natural selection and mechanisms of evolution. So these are the mechanisms of evolution that we discussed. I added symbiogenesis on here as another valid mechanism of evolution. These are all examples that we went through, so it'd be good to go through and make sure you can explain those. Specifically, natural selection obviously is like one of the most famous mechanisms of evolution. We talked about how you can recognize natural selection in action by running it through the VIST checklist. Is there variation in the population? Is that variation heritable? Is it selected upon either for or against by the environment? And then over time, does that variation spread through the population? We talked about the sneaky male salmon that mimic females up here and how they're able to still get the job done, and how they represent the whole sockeye salmon population represents an example of evolution by natural selection. Here's some other kind of practice questions from that same direct observation slide set that allow you to test your understanding of different mechanisms of evolution. So I would pause the video and go through these and make sure that you can come up with an appropriate mechanism of evolution. So if you pause the video, you should see that this population of 200 white-faced capuchins was hit by a tidal wave. All of them were likely to be wiped out. So if allele frequencies did change, then, sorry, this is not going to be the best writing, but genetic drift. I'm not going to write out the whole thing. Genetic, put D, looks like a P, but genetic drift. Because if they all had an equal opportunity to be wiped out, then there's no selective pressure happening here. In the case of B, you have a tribe where members are mating only with people of the same tribe. So a woman leaves, she like mates with a guy in another tribe, and then they come back to the original tribe. So if this changes allele frequencies in the population, you might argue that there are two mechanisms at work here. There's definitely sexual selection. There's some kind of preference exhibited in mating, and then there's also some migration going on, some introduction.